The next topic that we are discussing in inventory theory is quantity discounts. So actually, what happens if the supplier where we reorder our items that we put in inventory offers some quantity discounts? We have two types of quantity discounts that we want to have a look at here. The first one is the all units quantity discount. So what happens if we order 1 unit more and then we get a special price for all the units that we have ordered and not just that 1 unit where we exceeded the previous amount of where we would get a certain price for our items. So it's per item. And then we have another quantity discount that is the incremental units quantity discount that we look at after we have looked the all-in-ones unit quantity discount. So for the all units quantity discount, we have certain amounts of quantities that we reorder, and for each and every of these levels, until we reach a certain amount, we get a special price. So for instance, here for the first interval from 0 to Q2 units, we get a price C1. And then in the next interval, we get a price C2. And this is valid then for all the units that we order, not just for the ones that exceed the first level discount, but for all the units. So we have a function that with respect to the cost per item that look like this. If we look at the total cost function, then this results in a so-called step cost function, where we have the total costs that are decreasing with respect to the amounts that we order, and when we have reached a certain amount to reorder, we get a next price for all the units that we order. So we would go one step back, and then this is valid for all. So we have breakpoints here or jump points where until here we get a certain price, and then we would go down with all the units so that we would reach a new level. So the question is now, well, we are still facing a demand that we know, and we have still fixed ordering costs. We have purchase cost per unit item with respect to the demand, and we have our inventory holding costs that we need to balance somehow. So the good question is how much we should order with respect to our demand in case that we are granted some all-unit quantity discount. To answer the question, we have here an algorithm that helps us determining how much to order. That goes as follows. In step 1, we set our J to M, that is the number of discount levels. So we are starting with the highest number that in just the case that I have shown would be three levels with three different prices. So we would set J to 3, and then we would compute for the last price, so for C3, the optimal order quantity. As said, it is still dependent on our forecasted demand. So we would use the discount price that we are facing in the last level, and then compute the optimal order quantity. Then we would check if the optimal order quantity would be within this frame. So in this case, it would be Q3, that the optimal Q3, that we need to check if that is larger or equal to the one where we get the special price. If that is the case, then we have found the optimal solution. Otherwise, we need to set Q min to this level where we would reach the last price quantity discount, and then compute the costs accordingly. And then we would go to step 3. Then we would examine the next price level. That would be 1 unit below. So 3 minus 1 is 2. So we are computing then the optimal order quantity for the price C2. And then we would check if that is within the quantity frame where we get the price. If that is the case, then we compute the total cost with respect to this order quantity and compare it then with the one that we have determined when using the Q-min in step 1. If the total costs are smaller than this minimum cost that we have found, then we have found the optimal order quantity. Otherwise, we need to go further. And in case that this optimal order quantity that we have computed here is not within this quantity interval, then we compute once again, or we compute the total cost for that order quantity. And if that one is smaller than the minimum total cost that we have determined, we set the Q-min to exactly this order quantity. And if our yacht is larger or equal to 2, then we would repeat step 3. I can imagine that this sounds quite theoretical now, so we are going to regard the example that we have later on in our lecture slides for the parasol systems. So I'm jumping some slides to go to the parasol systems exercise. We have a company called Parasols that sells motherboards for personal computers, and they are offered quantities for their supplier for up to 25 units when they order motherboards. They get $350 per board. For quantities between 26 and 50, then they are charged $315 for each board. That goes beyond the 25 or the 26, and everything that is over 50, they get $285 per unit. So now there is a large communication firm that is expected to buy the motherboards for the next 10 years at a rate that is at least 140 per year. There is an order setup cost of $30. That is the fixed ordering cost or setup cost. And then we have a holding cost that is based on 18% of the annual interest rate. So here we have the inventory holding costs that are composed by the C multiplied by the annual interest rate E. So the question is now how much should be ordered. If we look now at the all units quantity discount, then I will show you how the algorithm works for that case using the whiteboard. So the first thing that we want to denote is the input data that we need for the all units quantity discount. We have price intervals where C1 is $350 for ordering a quantity that is smaller or equal to 25. The C2 interval is then we spend $315 for quantities that go from 26 to 50 units. And we have a price C3 that goes then for every other unit that goes beyond the 50, so from 51 and everything beyond, we get a price for all the units that we order, that is 285. So when we want to compute now the algorithm, the first step that we need to do is we set J equal to M, and M is now the last interval, or the last price, the highest, or the last price that we are charged. So it's 3. Now we compute the optimal order quantity for this price. I write everything out, that's so you get also the formula, and you know when what I'm setting in is input data. So we have the normal order quantity, and now this changes a little bit because this is our inventory holding cost that is compounded by the price per unit item and the annual interest rate. So the next thing is just setting in the input data, and when we do so, we get in the numerator 8,400 and in the denominator 51.3. And by the way, this is then our age. This is why I'm writing it out, so we can have a look at it. And this in total is then 12.8. Please be reminded that here we are not requiring the quantities to be integer, so we are regarding the continuous case, so it's absolutely fine to have a fractional order quantity. This 12.8 is smaller than the 50 units that we are required to order so that we get the price C3. Therefore, we need to go to step 2, or we go to step 2 now, and we compute the total cost of this order quantity Q3, which is 50. That is the interval where we get the price of 285. The total cost is given by C3 multiplied by D, plus, and this is the unit purchasing cost, composed by the setup costs or fixed ordering cost, K multiplied D, divided by the order quantity, plus the cost for inventory holding, that is the annual interest rate, multiplied by the price C3, multiplied by the order quantity, divided by 2, because we are looking at the average inventory holding cost. And if we set in now our input data, we get the following picture. And well, I'm gonna do it extensively once, and then you know exactly how this is done. So it's just recomposing the input data for once. And then I'm going to denote the cost splitted. So you see the quantities, it's 39,900 for the purchasing costs, plus $84 for the fixed ordering cost, plus $1,282.5 for the inventory holding cost, and this altogether is $41,266.5 as total costs when ordering a quantity of 50 units. Step 3 now is that we look at quantities below the the 50 where we get the last discount level. So we set j to j minus 1, which is 3 minus 1, which is 2. And we compute the optimal order quantity with respect to C2 now. Once again, I give you the formula so that you know which data I'm plugging in. And then I leave out something. And I'm finishing with 8,400. That is not changed because the 2KD has not changed, but our inventory holding cost has changed now. That is 56.7, despite the 51.3 that we had before. And I'm just highlighting it. So now our inventory holding cost is becoming more expensive. And we would be ordering now as an optimal order quantity 12.2 units. Before it was 12.8 and now it decreased a little bit. Step 3 was done. Now we look at step 4. That says now, we need to check if Q optimal 2 is within the feasible interval, then we have found the optimal order quantity. In our case, the 12.2 are far away from being 26 that we have as K2. So our optimal order quantity is not in the quantity discount interval of Q2 and Q3. That was between, we call 50 and 26 as values because we are far beyond that. So now we compute the total cost of that quantity, and that is as our minimum feasible cost that occur at Q2 is equal to 26, because that is the order level that we need to order in order to get the special price. So in this interval. And the total cost of K or Q2 of 26 is then given by the price C2 multiplied by D as our purchasing cost, then the fixed ordering or setup cost KD divided by Q, and then we have our C2 multiplied by the annual interest rate, this multiplied by the order quantity divided by 2. I do now a shortcut, so we get for the purchasing cost 44,100 plus the fixed ordering cost per unit is 161.5, and the inventory holding cost for these items is 737.1. So in comparison with the costs that we had before here, we see that we had purchasing cost of 39,900 for the units, Now this has gone up for the next price level, because that is straightforward. It depends on the C2, the price that we get. Then we see that beforehand we had a fixed ordering cost of 84. Now we have an ordering cost of 161. And for the inventory holding cost, so this got up as well. But for the inventory holding cost, this has actually sunk now. Okay, so the total of these costs, when we calculate them together, is in total 44,989.6, and this is bigger than Z min with the 41,000. So our Z min here is actually 41,266.5. So then we check in the algorithm if j is larger or equal to 2. If that is the case, then we go to step 3 for the next iteration 2. And actually that is the case, because our j is 2 and 2 equals 2. So we get to the next iteration. So we repeat step 3, where we set now j to j minus 1. Our actual j is 2 minus 1, so we set it to 1. Yeah, still have place here, so we calculate now the optimal order quantity for the price C1. Writing it down extensively, 2k d divided by C1 multiplied by the annual interest rate, and we get 8,400 divided by, this is now the last price, 350 multiplied by the annual interest rate, and this is 63 in total. So we are seeing that when we look at the inventory holding costs, of course, with each level or price level that we go below the one where we would actually get a better price discount, then our inventory holding costs also increase. So here we get then for the optimal order quantity for C1 11.6, and 11.6 is also well beyond the 26, but it is now in the interval for Q1 is actually in the interval for this price, that is Q1 and Q2, and Q1 is 0, Q2 is 25. So now we are in this level, and we compute then accordingly the total cost for that optimal order quantity. So that is now Z for our optimal order quantity is C1 multiplied by D for the unit purchasing cost, the total setup or ordering costs plus the inventory holding cost. That is now composed, or that is composed by the annual interest rate, and C1 multiplied by the order quantity divided by 2. And this is now $350 multiplied by 140. I do extensively once again. 30 multiplied by 140. And our optimal order quantity, 11.6. And this is plus the annual interest rate multiplied by 350 multiplied by the optimal order quantity and divided by 2. And this now is for the optimal, or for the purchasing cost, 49,000 plus the fixed ordering cost, 362.1. And for the inventory holding cost, 365.4. And if we compare these now to the levels that we got before, we see that the per unit purchasing cost once again goes up. The fixed ordering costs also go up from 161.5 to 362.1. And we see that our inventory holding costs have quite dropped, of course, because we would be in this case ordering less than half than what we would have to pay when we put 26 units into inventory. So we end up here with a total cost that is 49,727.5, and this is well greater than our total cost min that we have calculated in the beginning. So our optimal order quantity that minimizes our total cost will be Z min with a quantity of 50 units with total cost of 41,266.5. So although we have calculated that also when we look at our initial price that we have calculated when using the last or the best discount price, C3, we have calculated that in this case we would order up to 13 or 12.8 units with this point or with this price, and then we need to go up and up, but we see that the optimal order quantity ranges in between these 12 to 13 units when we round up. But despite all, the optimal or the minimum ordering costs in total are most favorable when we order 50 units. So although we just need up to 13 units, this discount pricing scheme would encourage us to order 50.